Hi, today we are looking at the first condition of equilibrium. This condition is that net force is equal to zero. So that means that our forces in all axes sum out to zero. Now, because there's no net force in any axis, that also means there's no acceleration of our object in any direction. We will utilize the following notation to show that forces are balanced both horizontally and vertically. So to show that our horizontal forces are balanced, we say that sum of Fx is equal to 0, and to show that our vertical forces are balanced, we use sum of Fy equals 0. Now solving these, to help solve these, we need to balance out forces in one axis and then focus on forces in another axis. Whatever axis we start with will depend on what forces we're given with to start. So we'll start looking at some examples. So in this example, we have a 600 Newton weight hanging off of essentially two cables, one that's horizontal and one that is coming down from the ceiling at an angle of 50 degrees. And we want to find both those tension forces. And like I mentioned, our tension one is horizontal, so it isn't taking any of the vertical force of a mass, which will help us when we get started with solving. So because it's not taking any of the vertical force, all of the vertical force is being taken by tension 2. So one of the first things I would do is change tension 2 into a triangle. So we know that tension 2 is acting on an angle, but we can split that into components that are both horizontal and vertical. So I have tension 2x and I've got tension 2y. Now, we're assuming that the object is not accelerating down and just staying there, so therefore we can say our sum of forces in the y direction is equal to 0. Now, acting in the y direction, we only have the tension 2y and our weight of 600 newtons, which we know is acting downwards. Now, if we rearrange this, we get tension 2 of y is 600 newtons. Now, if we look at our triangle that we've created, our 600 newtons is going to be opposite angle of 50, and we want tension 2, which is our hypotenuse. So therefore, we can use a trig ratio, more specifically sine, to solve for what tension 2 is. Now we know sine is opposite over hypotenuse, but we're trying to solve for our hypotenuse, so I would multiply both sides by the hypotenuse to get out of our denominator, and then divide both sides by sine of our angle. At this point, we can substitute our values in, and we get that tension 2 is 783.2 newtons. Now we still need to get tension 1. Now tension 1 is only applying horizontal force, so we'll look at our horizontal components. Now, because we're assuming it's not moving horizontally, we can say sum of forces in x direction is equal to 0, and we have two forces in x direction. We have the tension 1 as well as tension 2 in x direction. Now if we rearrange this, we get negative tension 2 in x direction is equal to tension 1. Now currently we don't know what tension 2 in x direction is, but we would know what tension 2 in the y is, and technically tension 2 as well, and we have an angle, so we could use trig. So I've chosen to use tan, so that would be my opposite over my adjacent. Rearranging this, to get our adjacent on its own, we multiply both sides by the adjacent to get out of our denominator, and then divide both sides by tan, and we get tension 2 in x direction is 503.5 newtons. Now, because we have said that tension 1 is equal to negative tension 2 in x, that means that tension 1 is 503.5 newtons as well. Okay, next example, we have this traffic light being held by two cables attached to a beam above, both cables have the same angle with the beam above. So some things that will help us with this is, in this case, both wires will split our force of gravity acting on the light equally because they both have that same angle. And we are finding the tension of those two cables. Now this is because the attachment angles are the same, so that's why our two tension forces will be the same. Okay, so first thing we're going to do is calculate the force of gravity acting on that traffic light. So we know force of gravity is just mg, so we've got 30 kilograms times negative 9.81 meters per second squared, giving us a force of gravity of 294.3 newtons downwards. Now if we look at our sum of forces in the y direction, we know they must equal 0, and that will have a y component of our tension 1 and a y component of tension 2 plus force of gravity. However, as we talked about on the previous page, since our theta 1 and theta 2 are equal, that means our two tension forces are equal. And if our tension forces are equal, then tension 1 in the y direction is going to be equal to tension 2 in the y direction. So if we take that equation that we had, we can replace tension 2y with tension 1y. And then at that point, move the force of gravity to the other side of our equation and add together our two tension 1y's. And then to get tension y on its own, divide both sides by 2, substitute our values in, and we get that tension 1 in the y direction is 147.15 newtons. So I've just split up the triangle at top, and we can see that for y direction we've got 147.15 newtons. That is opposite an angle of 35. We're trying to get our hypotenuse, so I would use sine. So sine we know is opposite over hypotenuse. If we rearrange this, we can multiply both sides by the hypotenuse and then divide both sides by sine of our angle, substitute our values in, and we get our tension 1, which we know is the same as tension 2. Okay, next example, we only find the tension in the two wires, and we have one wire being connected at an angle of 45 to the beam up top, and one at an angle of 37 to the beam up top, and we have a mass of 45 kilograms hanging down. Now in this case, our vertical force will not be split evenly because we do indeed have different angles. So we'll go over how to solve that. So if we look at this, we're going to have two forces in the x direction while we have three forces in the y direction. So I would start with the more simple with the two forces. So I'm going to start with my x direction. So we know sum of forces in x direction is 0. Now, if we break it down, we know that in our x direction, we would have tension 2 times cos 37, which would be that one's horizontal component minus the horizontal component of tension 1, which is T1 cos 45, and that's going to equal 0. At this point, we either want to isolate for T1 or T2. It doesn't matter which one. So to start, I have moved T1 cos 45 to the other side, and I have decided to isolate for T2. So I've divided both sides by cos 37. So I now have an equation for T2, which I'm going to utilize when we look at sum of forces in the y direction. So when we look at sum of forces in the y direction, we're going to have a vertical component of T1, a vertical component of T2, and the force of gravity acting on the mass. So vertical component of T1 is just going to be T1 times sine 45, or vertical component of T2 is going to be T2 sine 37. Now in that step, I'll put in my equation for force of gravity, as well as the equation we've come up for T2. At this point, I would move the mg to the other side of our equation, and then we're going to calculate these trig functions. So we'll figure out what decimal number is being times t1 in the first term, and then what decimal number is being multiplied by t1 in our second term. And we can substitute in our mg. So we get 0.7071 t1 plus 0.5328 t1 equals negative 45 times negative 9.81. We'll add together those coefficients in front of our t1 and multiply together our values on the right side of our equation. At this point, we can then divide both sides by the coefficient in front of our t1, and we get 356 newtons, which going to appropriate sig figs would be 360 newtons. So that's T1. Now to get T2, I'm going to go back to the equation we came up with for T2 earlier, and I will substitute our unrounded value of T1 into it. So we have 356 times cos 45 divided by cos of 37, which gives us 315 newtons, which rounding to appropriate significant figures gives us 320 newtons.